The idea behind the open feed water heater is that you have two streams mixing, a fairly warm, hot stream, a cool stream, and you're trying to bring up the temperature out at this so that the feed water is a higher temperature coming into the steam generator or the boiler. Okay, when you see something like this, take a look at the pressures. Is the pressure at 5 equal to the pressure at 2, which is the same because that's what the pressure of the incoming from the top? And is that equal to the pressure at 6? They all are the same pressures, right? So that's a key observation. And then you know that you have this notation y, 1 minus y, and it's back to 100% going out of the open feed water heater. And you should be able to write an energy balance for that open feed water heater. We did that last time, but when you do the energy balance, you have that you're bringing enthalpy 2, y, plus enthalpy 5, 1 minus y, equal to 100% times H6, true? So that y, you get an equation for y. All right. Well, with the purpose is that you want to, for the regenerative vapor power cycle, is to increase the temperature of the feed water going into the steam generator. Here is a closed feed water heater instead of an open feed water heater. Let's take a look at it. We have an inlet at the top and an exit at the bottom, and I'll call that the warm stream. That's the stream that's transferring heat away from itself and into another stream which is coming in at 5 and going out at 6. And these two streams don't mix. They don't mix. The warm stream typically stays on the shell side of a shell and tube heat exchanger. So you have a shell with tubes running through it. And the cool side, this liquid from 5 to 6, is in the tubes. So a typical shell and tube heat exchanger, and what happens is around the tubes there's vapor, maybe a two-phase vapor, but the vapor is going to condense on the tubes. When it condenses on the tube, it transfers heat into the tubes and it warms the liquid flowing through the tubes. Okay? So as it condenses, it'll form and collect the liquid at the bottom. It'll be a saturated liquid, and then you need to do something with that saturated liquid. In this case, the saturated liquid needs to be returned into the fluid stream. So there's a pressure drop from 7 to 8 across what they call a steam trap. The steam trap is a device that only allows liquid to go through. What it basically does is it senses the liquid level behind it. When it's sufficiently high, it opens, lets some liquid go through, and then it shuts off again before any vapor goes through. You want to hold back all of the vapor and make it condense. That's the purpose of the steam trap. And there's a pressure drop such that the pressure at 8 is less than the pressure at 7. Okay? So that's the steam trap. Well, let's do this. When we take a look at the condenser, how many inlets do we have to the condenser? We have inlet from 3, an inlet from 8, and we have one exit at 4. True? Talk to me about the pressures at each of these. Is the pressure at 8 equal to the pressure at 3 equal to the pressure at 4? Right. What constitutes a reason for a pressure difference? Turbines, there's a reduction in pressure. Pumps, there's a boost in pressure. And steam traps are basically a restriction. There's a reduction in pressure. But other than that, if I look at pressure at 6 and pressure at 1, is the pressure at 1 equal to the pressure at 6? It's just going through the steam generator. Steam generator adds heat, doesn't change the pressure. Likewise, when it goes through the condenser, all of the inlets and exits from the condenser have essentially the same pressure. Okay. Now, So now you know if you had maybe, just to throw out some numbers, a high pressure of 10 megapascal, an intermediate pressure of 1 megapascal, and a low condenser pressure of 10 kilopascal, you would know that, oh, the steam trap needs to drop it all the way down to P8 needs to be down to 10 kilopascal. Let's take a look at pressure at 2 versus the pressure at 7. Is the pressure at 2 equal to the pressure at 7, or is one higher than the other? The steam goes in, condenses, and the liquid is drained off at 7. The condensate is drained at 7. Is there any pressure difference between 2 and 7? No, they're both 1 megapascal. So the steam trap drops the pressure from 1 megapascal, in this case, down to 10 kilopascal. All right. Now, once we have the idea of the flows, we know it's not mixing in the closed feed water heater, and we also have a good idea of the pressures, then we can do an energy balance around this closed feed water heater. True? Okay, before I do that, I forgot to emphasize what are the mass fractions. You have 100% coming out of the steam generator going into the first turbine stage. It comes out and then some of it splits. The mass fraction that goes down to feed the feed water heater is Y. What continues? 1 minus Y, right? And then what comes out the second turbine? 1 minus Y. Okay. What comes out in 7 out the bottom on the shell side of that closed feed water heater? Y. What goes through the steam trap and goes out the other side of the steam trap? Y. So what's coming in is Y from the bottom. What's coming in from the top is 1 minus Y. So when it goes out at 4, you're back to 100%, aren't you? You're back to 100%. Then you're at 100% on the outlet of the pump, 100% on the inlet to the steam generator, and there you go. So you've traced your mass flows. You know, it's 100%, then it splits Y and 1 minus Y, but then they join back up. So that's going to be needed when we do the energy balance for this control volume around the closed feed water heater. What comes out of the hot stream? The hot stream is Y times H2 minus H7 is equal to what's going into the cool stream. That's H6 minus H5, and that's times 100%, so I'll just leave off that 1. Can you see that's a good energy balance? Now, the textbook gives you this equation in about that form, but it basically says we think your skill set is high enough that you can drive that. And you probably want to do it a little slower, but I think you can read this. This is what comes out, the rate of heat transfer, or the heat transfer going out of the warm shell side and going into the cool tube side. So what we get is Y, an equation for Y, H6 minus H5, H2 minus H7. Should we memorize that equation? No, just be able to rederive it when needed. Yes?
Are you gaining, wouldn't you be losing efficiency going through the steam trap because of the large entropy difference?
Okay, the steam trap is highly irreversible, and there will be a lot of exergy destruction in the steam trap. But there's another alternative. Let's turn to that alternative, and that alternative is to come out of the steam and come out of the shell side with the condensate, and instead of going into a steam trap, which is highly irreversible, put it into a pump to boost the pressure up. In my example, we had 1 MPa intermediate pressure. The steam trap drops it to 10 kPa. Maybe you'll take the 1 MPa condensate and you'll boost the pressure to 10 MPa and then mix that with what comes out here to feed into the steam generator. Now you look at that, you say, I can build a pretty good pump. That doesn't look like it'll have much exergy destruction. It looks like it's a better system. And it will be slightly better. But the problem is the pumps cost a whole lot more than steam traps. So there's more upfront cost. And so it's a trade-off. Complexity and upfront cost. and maintenance on a piece of equipment like a pump versus a steam trap. Okay? So there are different things you can do with that condensate on the shell side of the closed feed water heater. You can boost the pressure with a pump, or you can drop the pressure with a steam trap. Make sense? Very good. Let me pause. We can take a problem like this, okay? Here you see a steam trap, the closed feed water heater. I've listed the number of the states, right? And we can actually analyze it both by hand. Now it takes some work. It'll take some time to look up all the properties and jump back and forth, as well as do it by using Excel, a computer program. So what I would do at this point is to help you is to sit down and maybe try to solve as far as I can this problem right here with Excel. Does that sound good? But please make a note of this because I may have to refer back to it, okay? And what do we have? 1 is coming out. What is the pressure and the temperature at 1? It's 10 MPa and 440 degrees C. It expands to 1 MPa, so this is the 1 MPa, intermediate pressure at 2. Then some of it's diverted. How much? Y. Y is diverted. Remember the equation for Y we just derived? I think it's the same. Is it going to be H6 minus H5 divided by H2 minus H7? Okay. And then it drops to 10 kPa. It needs to be 10 kPa also at 8. And it's 10 kPa at 4. But what comes out at 4 is saturated liquid, is it not? Sat liquid. True? It's saturated liquid coming out of the condenser. Then it goes through our pump. One pump, so we're going to have the work going into the pump, just like we had the work out of the first turbine stage and the work out of the second turbine stage. And then what is the pressure at 5? Is it 10 MPa, 1 MPa, or 10 kPa? What is the pressure at 5? Well, it stays in the tubes, and then there's no pump from 6 up, so it's the same pressure as 6, and the pressure at 6 is the same at 1, so it's 10 MPa and 10 MPa. And then how about the pressure at 7? 1 MPa. Okay, so we got all our pressures right. Some of our temperatures are given, some are told us. Now, one thing about the feed water that leaves the closed feed water heater, you often have to have this temperature specified. In this problem, they say that temperature is 170 degrees C. All I can say is the temperature that this is coming out at. Okay, look at the saturated, the temperature at 4, saturated liquid 10 kPa. Maybe it's around 45 degrees C, right? It goes through the pump. Maybe it's 46 degrees C. A very slight increase in temperature. So what you're doing is you're heating up that feed water from 46 to 170. Well, in order to heat it up for the thing to work, you better have a heat source that's has a higher temperature than 170. That makes sense. And you can show that that the saturation temperature at 1 MPa to Tsat is, I think, around 180 degrees C. Tsat, okay? The saturation temperature. So when this steam comes out, saturated liquid at 1 MPa, what's the temperature at 7? About 10 degrees higher than the temperature at 6. That'll work. Okay, so this will come out at about 180 degrees C. You see what I'm doing with the temperatures? Let's say somebody says, oh, I want this to come out at 300 degrees C. Great, but you know what? If you do an energy balance, you may get a reasonable Y to make the thing work. But if you do an exergy balance, you may find that exergy is generated. Or if you do an entropy balance, you may find entropy is destroyed, which means you violated the second law of thermodynamics. But with these numbers, it appears very reasonable. And you'll find a lot of entropy generated in the closed feed water heater. It's a real system. It works. So with that, what I'm going to do is I'm going to rotate. And how many people would call themselves a novice, if not beginner, with Excel? Okay, then this is the perfect time that we need to talk about Excel, right? Okay, I want to solve this problem. First thing is to find Excel. Excel is loaded on all the computers in the ME labs. And so somewhere like here, you can usually find Excel right there. And then up and running it goes, okay? First of all, Excel is just a spreadsheet, and you have letter A, B, C designating, these letters designate columns, and numbers going down designate rows. So there's the column B, here is row 3, and a cell would be like B3, and there's even telling you the name of the cell that you've clicked in. And you can put comments, you can put text, you can put numbers in each of these cells. So if I wanted to put a number 2 in that cell, I hit 2, hit enter, and it's now entered. If I am now, it's moved me down, because that's typically what you do, enter numbers going down. You're in cell B4, maybe I entered a number 3. Okay. I can also enter equations, but when you start an equation, start it with an equal sign. So equal sign. And in the equal, I want to add 2 plus 3. And when I hit return, it knows I'm entered an equation and executes that equation and gives me the result in that cell. So that cell now has a value of 5. If I go back and click on that cell, up in this formula bar right here, it shows me what's going on. Oh, we have an equation starting with the equal sign, and I'm saying 2 plus 3. Let's go down to this cell right here, cell B6, and I want to start an equation. But this equation, I want to take 2 out of cell B2 or B3 and add it to this cell's value. So I click on that cell saying B4. Now I have an equation where I'm adding the value of one cell with the value of another cell and placing it in this cell. Hit enter, you get 5 again. True? And you can then say something like equal to maybe this cell, and if I want to square it, I can do times that cell again. I would square it. Or if I wanted to, I can come up and edit this here equation bar, do a squaring, whatever the syntax is for Excel to allow me to do things. True? And then it squares it. You can also have some built-in routines like square root. SQRT. You have to know what is the name. And when it's sensing that you're trying to type in a formula, it'll help you. Say, is this the formula you're trying to type in? It's like autofill, true? And let's say you don't know much about the square root and you want to be reminded. I can click on that. It's going to probably be slow right now. And it'll come up with help. It'll come up with help and it'll say, oh, here's, you're trying to get information about the square root of a number. And typically that helps even have a little example that you can work. Not much, it's not very difficult on the square root, is it? But there's some other things where you will be looking for that. I close the bracket, hit enter, and the square root of 5 squared is 5. Now, this value used the value out of cell B6, true? Notice what happens to cell B7 when I update B6, and I don't want it to be 6 anymore. Maybe I do this. I go back and I change cell B3. Maybe I change that to 5 or 4. Notice what happens to cell B6 and B7. It's updated. And so that's one of the beauties of the spreadsheet. When I start changing values, I don't have to remember. The equations will percolate through and update those for me. Now, let's say I want to take the hyperbolic tangent of this function. Hyperbolic. Sometimes they'll try and give me a guess. But this little function up here tries to help me find the function I want. And up here by the formula bar, I can type the insert a function when I'm looking for the function. So I can type maybe a question right here. It says hyperbolic something. I want it the hyperbolic. Oh, hey, we can do that. A sinh, that's a what is it? Arc sinh, the inverse hyperbolic sine. Sinh, I can do the hyperbolic tangent of a number. So there's a lot of built-in help, and that insert function key will help you find those things. All right. Well, if I come down here and I click on sheet, it'll move to a different sheet. I can go back to that sheet, but you can work on different sheets and get pretty complicated calculations going. But let's try and solve or set up the solution to the problem I had, okay? And so we had pressure in kPa, and we have temperature in degree C. Now, those are just text boxes as headers to a table. Now I'm going to put some numeric values in, 10,000 and 440, true? And maybe I would like to know what is the enthalpy in units of kilojoules per kilogram. That's all just a header, text box. And I come down, and if I had a routine, a function to help me calculate that, that'd be great. Well, I've loaded up with the help of other people in the University of Alabama software, which I show you how you can download and put on your own personal PC with that link right there in the design project handout. You just have to know the syntax. So we say, okay, I want to evaluate a function, start with an equal sign. I'm looking for the enthalpy. It starts to help me guess it, but there's just a whole lot built in, isn't there? But the syntax is usually an underscore with the pressure temperature underscore H2O parenthesis. That's my function. Click on the pressure, click on the temperature. Now, it assumes the pressure and temperature in particular units, kilopascal, degree C, and it gives back enthalpy in particular units. If you're ever at a loss, come up, you have that function right there, hit this function key, and it tells you, oh, you're trying to evaluate this function called H underscore PT underscore H2O. You're trying to give it a pressure in cell C5. The numeric value that I currently find in cell C5 is 10,000. You're trying to feed it temperature in cell D5. The current numeric value is 440. And you haven't put any comma with units because you can work in English units or pounds and BTUs, but I don't regularly do that. I leave it off. And currently, if this is to be evaluated right now, it'll return a value of 2,314. And down here it'll comment, hey, enthalpy in kilojoules per kilogram is a function of pressure in kilopascal and temperature in degree C. That's the SI units. And if you put the optional ENG for English units, then I want BTUs per pound mass for the enthalpy, PSIA for the pressure, and degree F for the temperature. So there's the resulting, that's repeating the information. So there's a lot of information available to help you. Let's evaluate entropy, lowercase s comma, kilojoules per kilogram Kelvin. And you would say S as a function of pressure temperature for H2O, and grab pressure, comma, click on temperature, and away you go. A lot of times I like to put what state it is, that's state 1. How did we go to state 2? Well, state 2 was 1,000 kilopascal, wasn't it? And it was isentropic expansion through that turbine, true? So the S2 is equal to that value of S. So, and if somebody says, no, it's not 11, it's now 11 megapascal, you put, and then it updates all the way through. But let's go back to 10 megapascal. Whoops. Okay, there you go. I want to get that enthalpy. Well, it's not a function of temperature and pressure and temperature. It's a function of pressure and entropy. Let's try that. Equal to H, a function of pressure entropy. And then, you know what, after a while you start to see it's highlighted. They want to help you fill it in. If you just hit tab right there that one that's highlighted is filled in. True. And then you hit this pressure, and I really need G6. I can type G6 right there, and it'll grab it and evaluate it. All right. Or I could do H as a function of pressure and entropy. Tab. Okay. I can grab this one, comma, and I can try to click on that like I clicked on this one. But the problem is it's hard. Sometimes I click in a box around it, then I kind of grab it and tuck it underneath. Anybody ever had that experience in Excel? Where you kind of want it underneath there. It's blocking itself. And so you just kind of get it there and then tuck it underneath. Otherwise, I found that very frustrating. There's another way of doing it. Just expand that thing way out here and then, oh, let's try it again. I want to evaluate enthalpy. It's a function of pressure and entropy for water. Hit tab. And there's my pressure, comma, and my entropy is, it's still covering it up, isn't it? I don't know why it's still covering it up, but I grabbed it and tucked it in, hit parenthesis and be done. Okay. What was state 3? Oh, also I like to put a little column out here about what properties fix that state. That was pressure and temperature, wasn't it, for state 1? Pressure and entropy for state 2. What about state 3? Didn't we go all the way to 10 kPa? 10 kilopascal. Is it entropy again? Isn't it isentropic expansion through the turbine? Okay, and now this is another beauty of Excel. If I've already typed that formula, I'm going to type that formula again, and what I can do is I can just do a Control-C on that formula, bring it down here with a Control-V paste, and it actually saves the relative location of the pressure and entropy, such that, let me hit escape, that this guy grabs it from this line for pressure and entropy, but this one, where I copied, it grabs the same line. It's on line 7 for the pressure at 10 and the entropy over there. So it's pretty smart. Ooh, we need to evaluate these temperatures, true? The other thing is I could evaluate quality, X. Well, let's do this. Let's do the quality as a function of pressure and temperature for the quality, pressure, and temperature. When it doesn't give me the formula like that, I have to look around a little bit, okay? Looks like I'm going to use pressure and enthalpy to get the quality. So I'm going to hit tab there. I'll get the pressure, comma. I'll tuck in the enthalpy, close it. And this is just a drawback a little bit. That quality comes in 1. That doesn't mean it's saturated vapor. It just is, they didn't want to put not defined, but that's definitely superheated steam. So you really need to be cautious. Excel is okay, but it's not smarter than you. It's actually dumber than you. And you have to know, oh yeah, this is they're just returning a number, not blowing it up and making it undefined like I can't continue. But I don't trust that. It's superheated steam. All right. Now let's do this. If I take and copy that formula and I paste it right here, I see the quality is 95% at state 2. If I paste it right there, it's 76%. If I want to have these look like percentages, come up to this number. It's under home, number, hit percent, and it makes it look like percents. If I want to adjust the number of digits, just adjust the number of digits. Similarly here, that seems like it's excessive number of digits. It cleans up my digits here. This looks a little excessive. Ooh, more excessive. So you can make it very visually appealing to you, and so it's easy to read. How about this? Let's get the temperature as a function of pressure and entropy. Will it allow me to do that? Sure. For steam. So there's the pressure, and here's the entropy. And notice that's coming in right there. I could also say, I'm just going to show you something. What is the temperature for saturated liquid? Ooh, it doesn't like that. How about sat? So I have to somewhat guess the routine. The temperature of saturated liquid is a function of pressure for H2O. And we'll use this pressure right here. And notice that temperature is the same as that temperature. So in the two-phase region, it's giving me back the saturation temperature. If I just grab this lower box right here on this cell, if I grab it right there and I drag it down, it brings that formula down. I could do cut paste or I could just drag it down. When you have a long column, a lot of times you drag a long way. Okay, so the temperature at 3 is 45.8. Let's get rid of this. What was 4? This was a pressure and entropy. What was state 4? That was coming out of the condenser. It's pressure and saturated liquid, wasn't it? So they say, how am I going to do that? Well, I can reference this cell right above. So it's 10 kPa, or I could retype it. And it's saturated liquid. I need that enthalpy. How about HL? Would that give me? Yeah, sometimes the syntax you have to think, okay, it's HL. Enthalpy of saturated liquid is a function of pressure for H2O. Come over at 10 kPa, close it. There you go. Too many digits, move it over. Okay, how about the entropy, saturated liquid as a function of pressure, H2O. Boom. There you go. And then you could put also the Tsat, function of pressure for H2O. Put the pressure there. See how you're building this out? How about quality? I guess we'll try quality. Do a copy, paste. Hey, it came in with 0%, which makes sense.
Is there any specific reason you're doing this on sheet 2?
Nope. And what you can do is go down here and click sheet 2, do a right click, rename the sheet and say main sheet. And then you don't like this sheet, click, come up, right click, delete that baby. So you clean up. You want to insert a column over here, insert. You want to insert a row right here, insert. So once you get good at inserting and moving things and making it clean up, and you can control. You can also delete, like I don't want those. Hit right, delete, bye-bye, or whatever. Now let's go to state 5. What was that? That was after our pump, wasn't it? It's going to be after the pump. Well, if our pump is going to boost us up to what pressure? 10 MPa. And here's the thing where doing it by hand will divert a little bit from the code. The pump is reversible, true? Is the entropy the same? It is. And here's the little advantage of the computer software, because now this state 5 is fixed by pressure and entropy, true? It's just like 2. What I could do is I could copy these 3 cells, just paste them right there, and it shows me, first of all, it's now compressed liquid, so 0%. That's just like 1 for superheated vapor. No, it's not saturated liquid. It's compressed liquid at 5. But there's the enthalpy calc, and there's now the temperature. Notice the temperature is slightly a little bit greater than the temperature at 5. There is a little warming. The temperature does go up a little bit, but not much. About what? Less than a degree. What is that? 0.3 degrees C. That's not a lot. Somebody says, I thought we were going to use V times, P 5 minus P4. You can do that. If you do that, I need the specific volume in units of meters cubed per kilogram. True. Let's go get the specific volume at state 4. V is a function of, V liquid. Does that work? Yeah, that'll work. As a function of pressure. So there's our specific volume. Notice the, it's a small number, 0.001010. That looks reasonable to values out of the table. And if we multiply that, so I want to evaluate V times the change in pressure, 10,000 kilopascal minus 10 kilopascal, I'll get the work of the pump. It's around 10.09 kilojoules per kilogram. True? Here, if I wanted to know the work of the pump, it's going to be the difference between this minus that. And if you do a little comparison of these numbers, they're not perfect, but they're good to almost 4 digits. So the way we were doing it by hand, VDP gives you 10.09. Doing it using this built-in software with constant entropy, it's 10.06. Close enough. As a mechanical engineer, at times you should say, good enough, right? Good enough, close enough. Let's go to state 6 now. What was state 6? That was coming out of the Feedwater heater, and it told us that it was at this pressure, and the temperature was it 170? So basically we're back to knowing the pressure and the temperature. I come up, I don't like to retype a lot, so I just grab those cells. Whoops. Hit escape. When in doubt, hit escape. I'm going to do this, and I'm going to do paste right there. So that evaluates the enthalpy as a function of pressure and temperature at state 6, as well as the entropy. What about state 7? What was state 7? Was that the saturated liquid coming out the bottom of our closed Feedwater heater? So it's pressure in saturated liquid. True? Okay, so the pressure was 1,000 and it's saturated liquid. Well, you could probably grab these right here, bring those down, and that'll fill it. So it's the enthalpy, the information we really look for is that enthalpy, and so there's that enthalpy. And you can compare it. Okay. Notice, what is the enthalpy of the sum of the steam that was diverted at 2? That came into the top of that closed Feedwater heater. What goes out is the enthalpy here. Look at the enthalpy difference. There was a lot of heat transfer from that warm fluid heating up the fluid, going from 5 to 6. All right. Let's continue on. What is state 8? Well, that was back to our low pressure and our enthalpy. True? Isenthalpic. So it's back to 10 kPa. And our enthalpy, what is our enthalpy? Is it 7? So there you go. Those two fix the state, knowing pressure and enthalpy. So I could look up temperature. Here's a question for you. Will that temperature be less than 180, greater than 180, or equal to 180? So we want to find the temperature as a function of pressure and enthalpy for water. There's our pressure. Here's our enthalpy. Last chance to guess before we go. Look at that. Why is it? And that number rings a bell. Hey, doesn't that number look familiar? Have I seen 45.8 before? It's actually two-phase. It's two-phase, state 8. And then you dump it all into the condenser, true? You dump it all into the condenser. So now that we have all of these, I have my property table figured out, true? I can maybe make this bold if I want. Bold. Clean it up a little bit with some pretty little formatting if you want, something like that. I'm going to do this. I'm going to grab all of this to the side and I'm going to delete it. Just hit delete key, it's gone. And I'm going to start my calcs over here. And one of the most important is that mass fraction that's diverted. What is the equation for that? Was it H6 minus H5 divided by H2 minus H7? Was that what it was? So it looks like for this problem, 27.17% is of the mass that's through the first turbine stage gets diverted down, leaving 1 minus y, which is simply 1 minus that. Now you say, why does it make such a simple calc? Often with spreadsheets like that, you just go ahead and evaluate that as 1 minus y. That way when I need it, I don't have to always do 1 minus something. It's available. It's 72.83%. Okay, let's do this. What's the work out of the first turbine stage? Was that H1 minus H2? All right. What about the work out of the second turbine stage? Is that H2 minus H3? Now, this one I'm going to put a little note. This is per kilogram going through the second stage, second turbine. Now, but I really want to put everything on per kilogram that went through the first turbine stage. So the work second turbine stage per kilogram of turbine 1, if that syntax makes sense to you. And what I do is I say, for every kilogram that went through the first turbine stage, only 0.72 kilograms goes through the second turbine stage. So I'm going to take this value and multiply by 1 minus y, and now I have that work that comes out on the same kilogram basis as this one. They are on the same kilogram basis. Subtle but important point. Then we go to maybe, what is it, Q in the condenser. So what is Q in the condenser? Let me back up and show a slide here. In the condenser, you can think about this stream being condensed and this stream being condensed, true? So Q of the condenser is the sum of two parts. It's the sum of 1 minus y times H3 minus H4 plus y times H8 minus H4. Okay. So let me go ahead and implement that equation in the Excel. So it's equal to 1 minus y times, it was H3 minus H4, true, plus y times H8 minus H4. Does that make sense? So this is how many kilojoules of heat is removed from the condenser per kilogram that goes into the first turbine stage. Let's do this one. What's the work of the pump? Well, is that going to be the H5 minus H6? That many kilojoules per kilogram? Yeah? Okay, take a look at the illustration again. 4 to 5. So 5 minus 4. Is that what I wrote? It's G6. You could if you double click this right here, it'll even highlight the box. Did I misspeak? Okay, I misspoke, but I got the right box. Thank you. All right, and then what's the last one? What is Q in the steam generator, right? And so it comes in and goes out. It goes out at H1, and it came in at H6. True? Is that right? Now, when you do this, calculate work net on the same per kilogram basis. Work net would be you have the turbine 1 plus the turbine 2 on the same per kilogram basis minus the work of the pump on the same kilogram basis. So it's about 1,003. How about Q net? And they better equal or I better look for an error. Because, yep, that's what it is. So it's going to be the Q into minus the Q out. And they agree. And kind of funny that it agrees to a lot of digits, doesn't it? It's nice to see. All right. What about the back work ratio? That's going to be the work of the pump divided by the net out turbine 1 plus turbine 2. And the thermal efficiency, what is that equal to? It's equal to the net work out divided by only the heat in, not in minus out. So only the heat in from the steam generator. And we could put both of those on percentage basis. And we find that it's 1% back work ratio and 40.3% on the efficiency for the plant. Well, we solved quite a complicated problem pretty quickly, did we not, in Excel? I'm going to post this up there, and hopefully that'll help you. If you're new to Excel, watch the video, pause it. Some students told me last semester it was great that way. See how you did it? Also, if you have any questions, John is available. Drop him an email. He also said he has a room available where there's a bunch of computers, and he's going to be there an hour on Monday. I think he said from 12 to 1 on Monday. Okay? And that's going to be in the 3rd floor of the engineering building. There's a bunch of computers. There's nothing like you sitting down at a keyboard, having to do it yourself, and somebody to help you right behind when you get stuck, okay? So John will do that. Drop him an email. Thank you for your attention, and we are done, huh? Enjoy the weekend.